Hey there! So we did it. We managed to ingest data to our data lake from various sources. Alright, but what next? Do we just create reports directly on this raw data? Or do we have to do something else? And if so, then why? And that's the topic for today, so let's get started. Alright, so our data is in a data lake. So let me draw it to refresh our memory how the typical BI solution might look like. So as always, we start with various data sources, and there might be of different types. Some files like some CSV, JSON, XMLs, you name it. Quite often we will also work with different types of databases: SQL Server, MySQL, Oracle, the ones located on premises, in a cloud, in a Google, Amazon, or Azure, doesn't really matter. Well, it does when you are doing the ingestion, but from the theory point of view, there is no big difference. And you also might have to work with various types of APIs, like we saw in one of previous episodes, when we were ingesting data from this replicable REST API. And we know already that we don't want to run our reports directly on the source data, for various reasons that were covered in one of the first episodes. So what we are doing in our BI solutions is like this. Well, we want to ingest this data and store it somewhere. And in our case, usually, the most often, we would use a data lake to store our data. So what we do is simply we develop the ingestion process. So those blue lines, they represent the ingest part of the whole solution. Alright, and we did it. Our data landed in the raw zone using a native format, original format, so we didn't do any data conversions, file format changes, transformations. No, as for now, data is in its native state. And what we would like to have at the end is different type of reports, because that's usually the goal of the whole BI solution, to give some insights for the end users. So what we might have might be different reports, some KPIs, some pie charts, whatever, different types of visualizations, the ones that would give the best information to the end users. So that's our goal. And now, do we connect those reports directly to our raw data? Is the data suitable to be used at this state? And the answer is no. Don't do this. I know it's tempting to do so, because you already have the data. So why bother with doing some additional steps if you can quickly deliver the results and have the reports ready? But this is at that end. Sooner or later, you will end up with various issues. Of course, if you have to create a proof of concept or a prototype of a report very fast, within a day or so, then yes, that's a valid point to connect directly to these raw data sources. But it shouldn't be treated as a long-term solution. But why? And there are multiple reasons why this data stored in our raw layer in a data lake is not a best choice to be used directly. So first of all, you will notice various quality issues with this data. And obviously, almost every time the owner of the data, of the source data, will say, my data is super clean, it's pristine, it's perfect, it can be used for reporting. But in reality, it's not the case. So for example, from quality point of view, you'll find a lot of data duplicates that you'll have to handle somehow. You might find data sets with missing data. For example, You might have a column that from business point of view should have some value, but it doesn't for some reason. Maybe it is some very old data set, or maybe someone made a manual migration and forgot about this stuff. Or maybe there was some error in data processing. Who knows? Also, there might be some cases when data is simply wrong, right? Even though from technical point of view this data is correct, its format, its types is fine, but the values are wrong. And you would have to discuss this with the business owner or with the data owner and ask questions why this data looks in this way and how should we handle it. And those quality issues, they happen in every project, so be prepared for this. And later on, I will show you how to handle this. So already you should see that this data that we just ingested into the raw layer, it will require some transformations to handle all those issues that I was just talking about. Then, apart from quality related issues, you might have some technical issues. So let me write it down. Technical issues. So for example, please remember that when we are ingesting the data, we use a native format. And some of those formats are not suitable to be queried in an automatic way. For example, Excel files. It's not that easy to run a query from some external system on an Excel file. It is doable, but it might require some additional setup or additional steps that are not that straightforward. Then, as we saw in the case of this replicable data that was read from REST API, the data was paginated. So pagination might be the issue. And let me show you how it looks like. So that's the data we got from replicable. And you can see that every page is just stored as a separate JSON file, separate JSON object. And we have to deal with it somehow and only read the parts that is interesting for us, those results object. And again, we have to somehow parse this concatenated big JSON file and read only the parts that are interesting for us. And also, please notice that we've got some data that was important for us at the time we were ingesting the data, those next pointers that were pointing to the next site. But once the data is ingested, we no longer care about this. So we would like to remove this data, just not to confuse reports, report builders, report users. And because if we leave this data in our data sets, they would start asking questions, what this next and previous fields are, how do I use them? And just to avoid this, simply remove this metadata that is not needed in our case. Then, actually, we didn't have this case when I was showing various ingestion patterns, but quite often it is the case that every day you load the same set of data, the same data source. And later on, you will end up with multiple versions of the same row, the same object. And somehow, you would have to decide which version of the row is the current one. Likewise, if you have multiple versions of the same row that changed over time. And again, here, it is super important to make sure to use a proper version that was valid at a given point in time, if you have to do this. Then, what other issues might prevent you from using the raw data directly. So again, PII data. Those sensitive information like first name, last name, email address, and so on. Maybe you have to make it anonymous in some way. Then, what is also very often encountered in BI solutions is that the data that we ingest from the source is simply too complex. Because think about this. One of the data sources that we connect to very often are various types of databases. And usually, those databases, they support this OLTP workload, online transactional workloads, which means that the structure of the database is highly normalized, like third or fourth normal form, which results in many tables that are connected using different relationships, and this design works in this transactional world. On our hand, when we want to start building the reports and we would like to give the model to report builders, we would like to make sure that the data model is simple, that it is easy to understand. And if we just expose the original model that contains hundreds of tables with different joins, various where conditions, it would be simply too difficult for report users to use. And as an example, think about SAP database and the structure it has. It's super complex to understand what those tables mean and how to connect them. So for sure, we want to somehow transform this original data model into a simpler one that would make further steps easier. Then, very often, on the data we just read, we have to apply some business logic to combine different datasets together or to make some transformations, like parse various columns into separate ones, make some conversions, and so on. So another issue is that no business logic was applied yet. And of course, it could be done on the fly in the reports side. But in the long term, it's not the best way, because then it would have to be repeated in every report. And we would like to move it to the error phase and just do it once and let other phases just to simply consume the outputs. Yet another issue that we might have is that various data sources are disconnected. And what do I mean by this? So let's say that we are ingesting data from multiple data sources, and all of them refer to a customer, but they might lack a common identifier of a customer. So even though each of them refer to the same physical customer, it might not be easy to connect those data sources and simply refer to the same customer. It might require some additional logic to be implemented. And again, it should be done here in a data lake and then just expose this stuff to later phases. So yes, so you can see that this raw data, it has multiple issues that we have to deal with before we start building reports. And that's something that we'll be doing over the next episodes. We'll be transforming the data just to deal with all those issues. So the way to fix this is to simply transform our data. Alright, but what should be the output of those data transformations? How do we make sure that we do it in a proper way? And well, let me help you with this. So some of the stuff we already covered. So we know that the data stored in a row layer, it uses the native format, CSV, JSON, Excel, whatever. But we already learned that the ultimate file format for our BI solutions is a delta. So for sure, we would like to make sure that our data is converted from the native format to this delta format. Then we know that we have to remodel the data to make it easier to understand. We would like to make it fast for end users. And again, if our source data it contains multiple tables that requires a lot of joins, then obviously it will be slow. So we have to make sure that the model that we will use will satisfy those requirements. And there are different modeling techniques that could be used. One that is, in my opinion, the most commonly used is called dimensional modeling. So what we would like to create is something called dimensional model. And I will talk about it today. Right, but why? Why do we want to create this dimensional model, whatever it is? So first of all, it is very easy to understand. And I will show it to you in some examples. So the business user who will start to use our reports and maybe create reports on their own, just using our data model, should be fine with it, with this task. So this dimensional model, it's easy to understand and use. Then it is quite fast to query due to the way it is built. We'll get to it later. For now, just trust me that that's the case. Then this dimensional model, it is really widely used. It became de facto a standard in data modeling. Now, this dimensional modeling is not the only way which we could use to model our data. There are other techniques as well, so let me just list them. So we have a Bill Inman approach, who created this, I believe it was called Corporate Information Factory modeling technique. We've got Data Vault, yet another technique that has some use cases in which this modeling technique is the best choice. We've got yet another one called One Big Table, in case of which we just dump all of our data into a big table that is later queried. But from my experience, the dimensional modeling is the most commonly used one, the one that is a standard in BI solutions. So that's the modeling technique that I will want to focus on. All right, but then great. So we would like to have this modeling done using dimensional modeling techniques. But how does it fit into our architecture? And actually, it fits very nicely, because honestly, no matter what design you choose, what architecture you would follow, at the end, you want to have this dimensional model created. And let me show it to you. So from one of the first episodes, when I was talking about those various data architectures, you should remember at least two cases. So let's say we would follow this modern data warehouse pattern, and that was the pattern in case of which we had this data warehouse created using some kind of a relational engine. Inside this data warehouse, we would have our dimensional model created using just database tables. And let's say that in this case, we just map the model inside our warehouse one-to-one to what we have in our data lake, which means that basically all transformations that would transform our raw data into this dimensional model would happen inside a data lake using some service that works pretty well on a data lake. And our data warehouse, this one, would be simply used as a SQL layer. So we would just load data to it, to its tables, one-to-one, without any additional transformations. And this approach, it might be used in cases when we have some data consumers here that have to connect using SQL language. And for some reason, they cannot do it directly to a data lake because they don't understand data lakes, but they do understand SQL. So that's one case. Another case might be that we still have our data warehouse, so this database where we have our dimensional model, but here we would do the transformation phase inside this data warehouse. Because again, you might think like this, alright, so I have this powerful data warehouse that is used to serve my data, but it's underused, it's underutilized, and I'm still paying for this. So maybe let's use its power to transform the data into the target state. And that's a valid approach. So in this situation, you would simply read the data from your data lake and use stored procedures inside your database to transform it into, again, this dimensional model. So at the end, you would have your dimensional model created inside your data warehouse. What differs is a place where transformation happens. So let's say those two cases, they represent this modern data warehouse approach. And let's say that we've got a third approach, in case of which we don't have a physical data warehouse. So let me draw it like this. So we have something called serverless data warehouse, in case of which the model, dimensional model, it exists inside our serverless data warehouse, but not physically. The serverless data warehouse, it simply points to our data located in a data lake. So the data is stored in a single place, in a data lake only, but it is exposed using SQL endpoint. So if we have any data consumers that have to speak SQL, well, they could use this serverless data warehouse without any issues, but the data would be, in fact, read from a data lake. And that's our lakehouse approach. Anyway, no matter which architecture you choose, what you will end up with is a dimensional model that is built somewhere in a physical data warehouse or in this logical one. But the model exists. So as you can see, it is really important to model the data in a proper way. Alright, so let's move on to this dimensional modeling, what it does, how it looks like. And now, please be aware that I'm not able to cover every detail of dimensional modeling within this episode. If you would like to learn more, then I highly recommend this book, Data Warehouse Toolkit by Ralph Kimball and Margie Gross. Kimball is the person who created this dimensional approach. A very good book, must have for you if you would like to go into this modeling. And even though this book was written like 30 years ago, many concepts from this book are still valid. So this book, it simply stood a trial of time. So from your point of view, it means that in many projects, you will encounter this dimensional modeling, so you have to know how it looks like. Now, depending on the company you are working for, as a data engineer, you might or might not be responsible for modeling the data. In bigger companies, there is a separate person, data analyst or data modeler, who would model the data, and you, as a data engineer, you would be responsible for filling this model. But if you're a one-man army, then it might be your task to implement everything, starting from ingestion through transformations, building the dimensional model, and finally the reports. So it really depends on your role. From the exam point of view, you don't have to know how to model the data, but you have to know how it works, and later how to configure various services depending on a type of a table you will be working with. But I will get back to it in a second. Alright, so what is this dimensional modeling? So let me give you an example, the one that is very widely used. And you should remember that we are switching from OLTP, this online transactional processing, into online analytical processing, right? That's why we are changing the data model. We are changing the way our data looks like to make it easy to understand and to make it fast when it comes to queries. All right, so let's say that we are modeling a system for some company that sells something, a very universal case. And we would like to measure sales, how much of a given product was sold in some period of time. So it naturally comes to your mind that we have to measure something, and we want to measure our sales. So let me write it down, that sales is something that we would like to measure. And in dimensional modeling, this becomes a fact. So this will be our fact table, the thing that happened and that we want to measure. So inside our sales fact table, you would have different measures. And measure is simply a number that represents something that you want to measure. So in our case, the very obvious cases might be, well, sales amount. So how much money was earned in a given sale, or how much it cost. So that's a first example of a measure. Then we might measure, all right, how many copies of a given product were sold. So quantity. We might have another measure, a thing that we want to measure and later analyze, like what was the margin of our sale. Or maybe what was the amount of tax associated with given sale. So all of this stuff is a numeric value that you would like to later analyze. Or maybe what was the discount amount that was applied in case of a given sale. Alright, so fact is simply something that you want to measure. But the problem is that we don't have any context right now. What this sales amount is linked with, what's the quantity, what kind of a product. So what we are missing here in our design are dimensions. So fact is a thing that we want to measure, and dimension is something that gives context to our fact. And dimensions, they simply answer the questions who, what, where, why, when, and so on. So in our case, in the case of sales, we might have something like this. So let's say we've got a product dimension that says, all right, so this was the product that was sold, that was associated with given sales. And to make this connection between our dimension, the green one, and our fact, the blue one, what we would have to do would be to store some kind of identifier inside our fact table that points to a specific product. So we might have this product ID, like so. Then maybe we would like to know, all right, but who bought this product? Who was the customer? So again, we might have yet another dimension called customer. That again would be linked with our sales fact. And to make this link possible, I would have this, let's say, customer ID field in our fact table. Then we might think about various dates that we want to grab together with our sales. So for sure we would need a date time dimension. And from our sales point of view, you have to think, all right, but what types of dates you might be interested in? So for example, the obvious one would be a sale date. Sale date. So basically, when given a sale happened. You might want to store or record other dates, maybe order date, if that makes sense in the context of your business. So when order was submitted. You might want to track a time when the order was delivered, like delivery date, and so on. Then maybe you would like to know who from your sales rep was responsible for this sale. So maybe you would have this yet another dimension called employee or sales rep that you would link with your sales fact that would be responsible for maintaining this sale. So this is your employee ID, and so on and so on. So you should already start to see the pattern. So in a central place, we have our fact. In this case, it is our sales, which indicate something that happened, something that you want to measure. And there are also various dimensions that surround our fact that give a context. And this type of modeling is simply dimensional modeling. So let me write it down that this particular instance, it follows a star schema pattern. So in a central place, we've got our fact, and we've got those dimensions surrounding our fact. All right, so this was one example of the model. And by the way, take a note how it differs from the model that you might find in OLTP solutions. So first of all, it is denormalized. Number of tables or data sets, to be more generic, is quite limited, quite low, compared to the original system. So for example, in your original system, you might have 10 tables that store data about customer. But here, in your analytical solution, you would somehow union it into a single table, just to make the model simple. The same with your sales. Maybe this data in your source system is spread across various places, but here you combine it into a single place, into a single sales fact. So this star schema, it is first of all denormalized, And you'll later see that with the normalization comes a lot of data redundancy. So various values are repeated over and over again in your dimensions, something that we want to avoid in a normalized modeling, like in those LTP systems. But here it is fine. And secondly, because the model is so simple, it is very fast to query. Because what usually happens is that you have to read your sales table and simply join it with those dimensions. And that's it. There is no complex logic associated with the joins. And finally, this model is super easy to understand. If you give it to an end user and say, hey, this is your sales. Here you can see those various sales amount, quantity, and so on, that you can slice and dice across those various dimensions like customer, product, employee, date, and that's it. And within a few minutes, your end user should be able to understand how it works and how to use it. So that's a huge advantage of using this dimensional modeling. That's why it is so widely used. And just to make it obvious, let me write it down that those green ones, objects, those are dimensions. So we've got dimensions and we've got facts. All right, so to give you more examples, let's focus on some other case. So let's say that I would like to create my own BI solution that analyzes performance of my YouTube videos. For some reason, I would like to do this. So how I might model it? Well, I might again create some fact table. Let me call it YouTube performance. And what things I would like to measure, what values I might be interested in. Well, maybe I would like to know how many times a given episode was viewed on YouTube. So let's add a measure called view count. Maybe I would like to know if the person who watched my YouTube video, whether it liked it or not. So let's use a flag, liked. Maybe I would like to know if the viewer subscribed to my channel after viewing a specific video. So again, I would like to have this is subscribed property or column inside my fact table. Maybe I would like to know how long my episode was watched, whether someone watched only a few minutes of it and then just dropped it, and maybe someone watched the full episode. So let me call it watch duration. And so on. There might be other measures that I would like to catch. Now, again, to make use of this model, I would have to add some dimensions to add the context. So, of course, I would need to have a dimension called video or episode that would indicate which video we are talking about. And to make this link possible, I would have to add this video ID field into my YouTube performance fact table. Now, if you're wondering, alright, but what would be stored in this video dimension? Well, it would simply contain various information about this video. So, for example, some kind of identifier that I would use inside my fact table. Maybe I would like to store a title of this video, maybe description, Maybe I would like to know what was the duration of the video. Maybe I would like to know if there were any age restrictions defined on this video, and so on. So various properties that describe my YouTube episode. Then what probably I would like to gather inside my model would be information about a viewer. So basically about you. Who are you? And here, to make it possible, I would have this viewer ID field that would be linked with my viewer dimension. And here inside this viewer dimension, I would have some kind of ID. Maybe I would have your YouTube login. Maybe I would have information about your gender, about your country of residence, and so on. And later on, I would be able to run various analyses. For example, is my YouTube channel popular more among men or women? Or maybe what country gets the most views, right? And maybe based on this information, I would change something in my channel. Then obviously, I would like to know when someone watched my episode. So probably I would link it with some date-time dimension. And by the way, take a look here. What I just did, I reused the same dimension that might be used in a different star. And that's totally fine. That's one of the core concepts by Kimball, is to create this, he calls it conformed dimensions. Dimensions that mean the same thing across your whole business, and simply plug various fact tables into the same set of dimensions. And that's what I just did. We have this common date-time dimension that can be used for our sales and for my YouTube performance facts. And to make it work, probably I would add a column or a property called view date or something. Then maybe I would like to analyze this YouTube performance based on device that you use to watch it. Whether it is a computer, mobile, tablet, and so on. So this would be my device ID field, and so on and so on. So this is how dimensional modeling looks like. And again, at this moment, you don't have to know how to model your data. Probably in time, it will become natural to you. But for now, you have to know what is a fact and what is a dimension and how do they differ from each other. All right, so let's move on. So far, what I was showing was this star schema, when we have this central fact table surrounded by dimensions. And actually, let's take a look inside this product dimension, how it might look like. So what we would probably have would be something like ID, then maybe product name, then maybe product subcategory, and maybe a product category. Of course, it depends on the business for which we are modeling our solution, like so. And let's say that we already have some data inside our product dimension. Let's say we've got a row number 1. It is some kind of a helmet. Let's say that we sell bikes. We're an AdventureWorks company. Helmet. Subcategory, maybe it is called bike accessories. category, I don't know, hobby, maybe, or however it is called inside our system. Then we might have yet another row, maybe some kind of, I don't know, gloves, that are again from bike accessories subcategory and from hobby category. Then we might have yet another product, in the case of which those categories and subcategories values will be the same. So you might already see that because our data is denormalized, you might have a lot of data repetitions. Probably in your OLTP database, you would have a different table for subcategory and different for category, because that's what we want to have inside our OLTP database. Here in BI solutions, it is different because we want to avoid those complex joins that might be slow and that might confuse users. So in our case, let's say that the product dimensions looks like this. You might run into some issues with this design. So let me give you an example. So let me repeat the design that we had previously. So we've got this sales fact, and then we've got the different dimensions that are surrounding it. And maybe one of them is this product. And this works just fine. But what if we have yet another fact? Maybe let's call it sales budget. Oh, let me use a different color just to be consistent. Sales budget. And basically by sales budget, I mean what is the target, maybe quarterly target, defining how much sales it is planned to be done for a given product category. And please note the difference. The granularity of our product dimension is set at specific product, so very granular. Contrary, the granularity of our sales budget is probably lower, which means that I guess it might be set at the category level, because I don't believe that managers set budgets for specific products. No, it's too granular. They operate on different levels. So if we would like to now connect this sales budget with our product, then we got an issue, because this product, it operates on a different level of granularity than our sales budget. And one of the solutions that can make it work is to change our dimensional model from this pure star schema into something called Snowflake. And Snowflake simply means that, alright, we will normalize our dimensions a bit. So instead of having this one big table that contains this natural hierarchy, product, subcategory, category, we would split it into separate dimensions. So maybe you would have something like this. We have a product dimension, then we have a subcategory dimension, and we have a category dimension. Like so. And obviously, in our product dimension, we would remove this data because it no longer belongs to the product dimension. Instead, we would add to a product dimension a value indicating which subcategory it belongs to. Then in our subcategory, we would have data about subcategory, like its name and so on, and information about the category and so on. So our design would no longer contain this direct link from sales budget to product. No, we would have these links between our dimensions, and we would link our sales budget with category dimension, because that's the granularity that is valid in this case. And this type of design, when you have these linked dimensions, it is called Snowflake. Snowflake. So this is Snowflake. So no longer we have this pure star schema with a central fact table surrounded by dimensions. Well, we still have the central fact table, but here those dimensions that might be connected to some other dimensions. That's the Snowflake design. And again, you have to be aware of this difference. I know it's a lot. If you feel that it is too complex, too difficult, don't worry, don't panic. It will come with time, the understanding of how it works. And again, this book is your friend if you are into dimensional modeling. All right, one more thing that I would like to talk about is a comparison between facts and dimensions. So let's say that we've got our fact table and we've got our dimensions. So how do they differ? Well, let's analyze them from two points of view. So first of all, when it comes to number of rows, it is totally fine and usually expected that fact table is way bigger when it comes to number of rows than a dimension. And it makes sense, because let's say that you are measuring your sales. Every day you would have a sale, right? But on the other hand, your dimension, your product, it doesn't grow that fast. You have a limited set of products that you sell, maybe 1,000 of products. But it stays mainly the same, with the same range of values. But the sales, with every new sale, a new row would be added to your sales fact table. And that's the reason why your fact table is usually way bigger when it comes to rows than a dimension. And honestly, if you take a look at a data warehouse that employs this dimensional modeling concept, it is not uncommon to see that from data warehouse size point of view, your fact tables will use, let's say, 90% of the whole data warehouse size, while dimensions, they took only 10%, maybe 20%. So when it comes to performance optimization, later on you'd focus on facts, and I will show it to you later on. Now, so this was comparison from rows point of view. On the other hand, when it comes to number of columns, it's the opposite. Usually, dimension has more columns than a fact, because dimension, it describes something, like describes your product, and it's not uncommon to have 100 different fields that describe your product. On the other hand, in your fact table, well, you only have your keys to your dimensions and your measures, and that's it. So that's how those two different tables differ when it comes to number of rows, number of columns. All right, and basically that was it. It's not everything that I will cover around this dimensional modeling. There are some things that I will leave for the next episode. What I would like you to remember from this episode is that this dimensional modeling is basically the thing that we want to end up with when it comes to various transformations that we will do with our data. So no matter what architecture you will choose, you will most likely end with those facts and dimensions that will be later consumed by your reports. Of course, depending on your choices, you might create those facts and dimensions in different places. But at the end, that's what you want to have. And that's it for today. I hope it was useful. Thanks for watching and see you next time. Take care.